So now we are on the back side of your PLQ2 worksheet, and we are going to be talking about intermolecular interactions. So inter, between different molecules, versus intra on the other side of the sheet, which was within molecules. So the first video that we did for this worksheet was talking about like within a single molecule, how do the atoms interact with each other? And then this side of the worksheet is talking about how if there are two molecules inside of a cell or inside of your body, how do those two molecules interact with each other? And there are three main ways that this is going to happen. We have van der Waals interaction, hydrogen bonding, and ionic bonding. And you should recognize this one as the same name as on the other side of the sheet, and the same rules apply there. So let's go ahead and actually start on the right-hand side and work our way to the left. Okay, so charges of the atoms involved. They are both, you can already guess, going to have what characteristic? Yeah, fully charged. Fully charged. So for something to be ionized means it's full pos or full neg. And again, another hint, like just how you're going to be able to recognize this when you see it in a molecule is it's always going to be indicated by a little plus notation or a negative notation. If you see that, it's a dead giveaway that you're looking at an ionic interaction. A hydrogen bond, in those interactions, these are going to be similar to polar covalent bonds. So in fact, atoms that are involved in polar covalent bonds are apt to form hydrogen bonds between molecules. And so those are going to be both partially charged and so you can imagine a delta positive and delta negative. And again, I'll do my notation down here. Remember, delta positive meant partial positive charge, and delta negative meant partial negative charge. And then van der Waals interactions. So if we've already covered the bases of fully charged and partially charged, then what's left? Neutral. Yeah, so in a van der Waals interaction, one atom is neutral, and the other is either neutral, what's going on? Neutral or polar or ionic. So if one of the atoms involved in an intermolecular interaction is neutral, then van der Waals is going to be the way it's interacting with its neighbor. It doesn't matter if the neighbor is fully charged, partially charged, or also not charged, van der Waals is going to be the way to go there. If both are partially charged, one positive, one negative, then we're looking at hydrogen bonding. And if both are fully charged, positive and negative, then we're looking at ionic bonding. Some examples of bonds between different molecules or different parts of the same molecule. I'm going to draw out some molecules here for you, and I'll do them in different colors just so you can tell like what's one molecule and what's another. Let's say in this first example, we're looking at water, H2O. Within the water molecule, what type of bond would bond together an oxygen and a hydrogen? What intramolecular bond happens here? Polar covalent, yes. So non-polar covalent, remember, that's when you want to look for carbon to carbon or carbon to hydrogen. You don't see that here. And so we are looking at a partially charged set of atoms here. If I added that notation, we'd be looking at a partially negative oxygen because it's a big electron hog, a partially positive hydrogen, and another partially positive hydrogen there. And then the neighboring molecule, let's just say there's like a methane over here. So a carbon bound to a bunch of hydrogens. And there you go, one of the ones you always want to recognize. A carbon to a hydrogen bond is a non-polar covalent bond, no charge here. So we have a lot of neutral atoms in this molecule. And if we want to think about how, say, these two hydrogens interact with each other, it's going to be van der Waals. So because this one is neutral, the only interaction that we're going to see happening here is a van der Waals interactions. And van der Waals interactions are low stability, and they're pretty fleeting. They don't last very long because there's not that cardinal rule being followed there. We don't have a partially positive attracted to a partially negative. We don't have a full positive attracted to a full negative. We've just got this neutral atom kind of hanging out near another atom. And so this is actually going to be our weakest intermolecular interaction. So van der Waals doesn't last very long. All right, let's do a hydrogen bonding example. And I'm going to make my first molecule water again. well, it helps if I draw it correctly. All right, so we've got oxygen bound to 2 hydrogens, and just like last time, I'm going to fix that bond because it's pretty messy. Just like last time, we have polar covalent bonding happening in the water molecule. We have unequal sharing of electrons between that oxygen and those hydrogens. The oxygen is a big electron hog, so it is partially negative, and the hydrogens are partially positive. And let's go ahead and pop it next to another water. Let's go ahead and pop it next to another water molecule, another oxygen, attached to 2 more hydrogens, and the same rules apply here. Because there's polar covalent bonding within water molecules, these hydrogens are partially positive, and this oxygen is partially negative. Water is like a tiny little magnet. And so if we want to think about how this hydrogen in one water molecule is interacting with the oxygen in the neighboring water molecule, that's going to be a hydrogen bond. You've got a partially positive hydrogen attracted to a partially negative oxygen. You've got opposites attracting here, and so you have kind of a mid-range level of stability. They are quite happy to stay in that interaction. And in fact, as we're going to talk about, or as we have been talking about in the videos, this is what gives water its surface tension. Because water molecules are attracted to each other in this way, it kind of literally holds on to itself and allows it to stay together. And so if we want to then think about an ionic bond, let's think about maybe a carbon that's bound to an oxygen and a hydrogen, and then maybe an ionized oxygen here. So we've got a fully negative oxygen right there. And again, it's indicated by a full negative charge. That's your giveaway. And maybe that's next to a neighboring molecule that's like a positive nitrogen bound to a couple of hydrogens. And so you're going to have this attraction between a fully negative and a fully positive atom happening here. And this is going to be high stability because you've got full positives near full negatives. These are the main 3 that you'll encounter. And again, the giveaway is going to be either seeing a full pos and a full neg and knowing it's ionic because you see those notations there, or seeing carbon to carbon or carbon to hydrogen bonds and knowing one member is neutral, so it's van der Waals. But honestly, the main one we're going to come back to over and over and over again is hydrogen bonding. The main one we're going to come back to over and over and over again is how water interacts with molecules in our bodies and in our cells. Remember, 2/3 of a cell is water, and water is able to form hydrogen bonds with hydrophilic molecules. So when we talk about something being water-loving, we're talking about something being able to form hydrogen bonds with water. And then I forgot down here, notation, ionic bonds are the strongest. All right, so really the main one here, the important one, is the hydrogen bonds. And we're going to talk a lot more about hydrogen bonding and hydrophilic versus hydrophobic interactions throughout the rest of this course.